It is a strange thing to spend decades building a machine that may live for only a handful of years. Stranger still when that machine is sent so far from Earth that once it begins to fail, we may never touch it again. And yet scientists were willing to risk all of that for a single reason. They believed this telescope could look so far into space that it would begin to look backward through time itself. Not metaphorically, but literally. It might show us galaxies forming near the dawn of the cosmos. And if that is true, then what Webb sees may force us to confront not just what the universe is, but how much of its beginning we may have misunderstood. The James Webb Space Telescope is often described as the most powerful space observatory ever built. And that is not an exaggeration dressed up for dramatic effect. In scale, complexity, sensitivity, and ambition, it stands apart from every telescope that came before it. It was named after James Webb, the National Aeronautics and Space Administration administrator who oversaw the Apollo era, but its purpose reaches far beyond the moon and even beyond our own galaxy. This is a machine designed to pursue one of the oldest human desires imaginable, to see where everything began. For many people, Webb first entered the public imagination as the successor to Hubble. That comparison is understandable, but it can also be misleading. Hubble transformed modern astronomy. Since its launch in 1990, it has shown us pillars of gas where stars are born, measured the expansion of the universe with extraordinary precision, and given us views of distant galaxies that reshaped how we picture the cosmos. But Hubble was built mainly to observe visible light and ultraviolet light with only limited infrared capability. Webb was built for a different task. Its real strength lies in the infrared. That may sound like a technical distinction, but it is the key to the entire mission. If you want to understand why Webb had to exist, you have to understand what the universe does to light over unimaginable distances. Light moves incredibly fast, faster than anything else we know, but it does not move instantaneously. It takes time to travel. That simple fact means every act of looking is also an act of looking into the past. When you look at the sun, you are not seeing it as it is at that exact moment. You are seeing it as it was a little more than 8 minutes ago, because that is how long sunlight takes to cross the distance between the sun and Earth. The same is true for everything else in the universe. The nearest star beyond our sun appears to us as it was years ago. More distant stars appear as they were decades, centuries, or millennia ago. Entire galaxies appear as they were millions or billions of years in the past. The farther out you look, the further back in time you go. This means the universe offers something that almost feels impossible. It preserves a visual record of its own history. Not all of it, not perfectly, and not in a form that is easy to read, but the principle is there. Somewhere, out in the vast darkness, light is still traveling toward us from the earliest galaxies that ever existed. If we can catch that light, then in a real sense, we can witness a younger universe. That idea alone would be enough to justify extraordinary effort. But there is a complication, and it is one of the deepest reasons Webb had to be designed so differently from Hubble. The universe is not static. Space itself is expanding. Galaxies are, on average, moving away from one another, and the more distant they are, the more strongly that expansion affects the light they emit. As light travels across the stretching fabric of space, its wavelength is stretched with it. This is known as redshift. To picture what that means, imagine a wave being pulled longer and longer as it travels. The color of visible light depends on wavelength. Stretch the wavelength enough, and the light shifts toward the red end of the spectrum. Stretch it further still, and it moves beyond visible red entirely into the infrared. So if the earliest galaxies are incredibly distant, and if their light has been traveling toward us for more than 13 billion years, while the universe expands all the while, then much of the light they originally emitted will no longer arrive as visible light. It will arrive in infrared. That is the problem Webb was built to solve. If Hubble was a great eye for the visible universe, Webb was designed as a way of seeing what visible eyes miss. It is not simply more powerful in a generic sense. It is tuned to a different reality. It is meant to detect ancient light that has been stretched, cooled, and dimmed almost beyond recognition. Infrared light offers another major advantage as well. Cosmic dust, which blocks or scatters visible light, is often much less effective at hiding what lies behind it from infrared observations. Regions that once looked opaque can become partially transparent. Stellar nurseries buried inside thick clouds can begin to emerge. Structures hidden within gas and dust can reveal themselves. In this way, Webb does not just look farther. It also looks through things that once stood in the way. But seeing in infrared is difficult. The signals Webb is hunting are extremely faint. Light from the earliest galaxies has traveled for staggering distances. It has spread out, weakened, and been altered by the journey. To collect enough of that light, Webb needed a mirror far larger than Hubble's. That is why its primary mirror spans 6.5 meters across and is made of 18 hexagonal segments coated in a thin layer of gold. Gold is especially effective at reflecting infrared light, and the size of the mirror gives Webb a huge collecting area. More area means more photons captured. More photons mean the difference between silence and a detectable whisper from the deep past. That mirror is one of Webb's defining features, not only because of its size, but because it had to be folded for launch. No rocket fairing available could carry the observatory in its full operational form. Webb had to be designed almost like an enormous mechanical flower, packed inward for the journey, and then opened in space through a long sequence of deployments. Its mirror wings would fold out, its sun shield would unfurl, its support structures would extend and lock into place. Everything about the mission depended on those mechanisms working correctly the first time. And that is part of what made the telescope so nerve-wracking to build. Hubble, for all its brilliance, occupied a kind of privileged position in human spaceflight history. When a flaw was discovered in its optics after launch, astronauts could visit it and repair it. Later servicing missions upgraded its instruments and extended its life. Webb will never enjoy that luxury in any practical sense. It travels far beyond low Earth orbit to the second Lagrange point, a gravitationally stable region about 1.5 million kilometers from Earth. That is far enough that routine human servicing is not part of the mission plan. Once Webb is there, it is largely on its own. That reality changed the nature of the engineering challenge completely. Every latch, hinge, motor, sensor, cable, and deployment sequence had to survive years of development, intense testing, the violence of launch, and the unforgiving conditions of space. There were countless opportunities for failure. A membrane could snag, a motor could stall, a segment could fail to align, a thermal imbalance could interfere with the optics. In a mission this intricate, success was never just about building a powerful telescope. It was about building one that could become itself after launch. And while all of that would already be difficult, Webb carried an additional burden created by the very light it was meant to observe. Infrared radiation is heat. Anything warm emits it. That includes the sun, the earth, the moon, and the telescope itself. If Webb grew too warm, its own heat would begin to swamp the faint infrared signals it was trying to detect. It would, in effect, blind itself. So Webb needed to stay extraordinarily cold. Not just cool by ordinary standards, but cryogenically cold. That is why the observatory carries its enormous 5-layer sun shield, a structure about the size of a tennis court when deployed. The sun shield blocks heat from the sun, earth, and moon, allowing the telescope and most of its instruments to cool to temperatures so low that their own infrared glow becomes manageable. On the hot side, facing the sun, temperatures can soar. On the cold side, where the instruments sit, temperatures plunge deep below anything we experience naturally on Earth. This is also why Webb's location matters so much. By operating near the second Lagrange point, the observatory can keep the sun, earth, and moon in roughly the same direction. That allows the sun shield to protect the telescope continuously. It creates a stable geometry for cooling, power generation, and observation. It is a beautifully elegant solution, though one purchased at the cost of distance and vulnerability. The telescope's lifespan reflects that compromise. Webb carries enough fuel to maintain its position and orientation for a limited period. In broad terms, the mission was built around a working life measured not in decades upon decades, but in something closer to 1 decade. For a project that took roughly a quarter of a century to develop and cost nearly $10 billion, that can seem almost absurd. How can something so expensive, so delayed, so difficult, and so fragile be considered worth it if it will not last forever? Because forever was never the point. What scientists needed was not a permanent monument in space. They needed a brief opening into a region of cosmic history that had remained largely inaccessible. They needed an instrument sensitive enough to catch ancient infrared light. They needed a telescope that could peer through dark clouds and study the chemistry within them. They needed a way to examine the atmospheres of distant worlds, the structure of star-forming regions, and the earliest large-scale architecture of the universe. In other words, they needed not longevity for its own sake, but capability unlike anything before it. And capability like that does not come cheaply. Webb's story is filled with redesigns, budget growth, political pressure, and moments when cancellation felt frighteningly possible. Early visions of a next-generation space telescope were far less ambitious. But as the scientific goals sharpened, it became clear that reaching them would require more than incremental improvement. A truly large infrared telescope in space demanded new engineering, new compromises, and a degree of patience that often seemed almost unreasonable. Yet the deeper truth is that astronomy has always advanced by asking whether a new instrument can reveal something fundamentally inaccessible to the old one. Galileo changed our place in the cosmos by turning a telescope toward the sky. Hubble changed our understanding of scale, age, and structure by moving a telescope above the atmosphere. Webb was built on that same logic. If the early universe has hidden itself in redshifted infrared light, then only a telescope like Webb can go after it directly. And that brings us back to the paradox in the beginning. A machine can be temporary and still be transformative. It can be delicate and still alter science forever. The real measure of Webb was never going to be how long it survived. It was always going to be whether it could reach a depth in time and a precision in observation that no other observatory had ever achieved. Before it could answer those questions, though, it first had to survive the far more immediate danger of becoming a masterpiece of engineering that never truly awakened at all. Because for Webb, the path to seeing the first light in the universe began with the terrifying requirement that an impossibly folded telescope unfold perfectly in the dark. Because that unfolding had to happen in hundreds of precise steps, the suspense around Webb did not end when the rocket left Earth. In some ways, that was when the real tension began. A launch is violent, but it is brief. Deployment is quieter, slower, and far more unnerving. Over the following days, the observatory had to transform itself from a tightly folded payload into a functioning scientific instrument spread across space with almost impossible delicacy. Each successful maneuver brought relief, but each one also exposed how much still had to go right before the telescope could begin the work it was made for. The antenna had to swing into place so Webb could speak to Earth. The solar array had to deploy so it could power itself. The tennis court-sized sun shield had to unfurl, tension, and settle into the geometry needed to keep the telescope cold. The mirror tower had to extend. The side wings of the primary mirror had to fold out. Then, once the structure existed in its final form, the hard part continued. The 18 mirror segments had to be aligned with astonishing precision so that they behaved not like separate pieces, but like one coherent optical surface. That process alone reveals something important about modern astronomy. When we picture a telescope, we often imagine a passive instrument, a silent tube pointed at the sky. Webb is nothing like that. It is an active, finely tuned system that had to become sharper by degrees, learning to focus itself after reaching space. At first, stars appeared as 18 separate points because each mirror segment was reflecting its own slightly offset image. Then, through careful calibration and adjustment, those points began to converge. One by one, the segments were steered into alignment until the telescope could produce the kind of crisp, stable observations its mission demanded. Only then could Webb begin to show us what all that effort had purchased, and almost immediately it became clear that the answer was not simply better pictures. The first public images were beautiful enough to command attention across the world, but beneath their visual power was something far more important. They were demonstrations that the telescope was seeing in a fundamentally new way. Webb was not just gazing at familiar objects with more detail. It was exposing structures that had been hidden from view, pulling depth and texture from places where older telescopes had often encountered a veil of dust. One of the most striking early examples came from a region in the Carina Nebula, sometimes called the Cosmic Cliffs. Even the name feels almost too dramatic, and yet the image justifies it. Vast ridges of gas and dust rise like mountains against a field of stars, lit from behind and within by newborn suns. At first glance, it looks like a landscape, almost geological, as though we are seeing cliffs on some impossible alien world. But that impression is an illusion of scale. These are not rock formations. They are walls of interstellar material stretching across light years, shaped by radiation, winds, gravity, and time. What makes this view so scientifically important is not merely its grandeur. It is the way Webb reveals the dynamic relationship between stars and the clouds that create them. In visible light, many star-forming regions appear partly obscured, with dust acting like a curtain. Infrared observations change that. Webb can peer through much of that dust and expose the young stars nestled within. Some of them appear as brilliant points with diffraction spikes. Others are still wrapped in dense cocoons. Jets and outflows can be seen punching through the surrounding material as newborn stars begin to assert themselves against the environment that formed them. This is where the telescope's ability to see through dust becomes more than a convenient technical feature. It becomes a way of witnessing a process that defines much of cosmic history. Stars do not simply appear. They emerge from cold clouds of gas and dust that collapse under gravity. As denser knots form, material falls inward, heats up, and eventually reaches the conditions needed for nuclear fusion. But that transformation is messy. It happens inside crowded, turbulent regions where winds from massive stars can both compress nearby gas and erode it away. New stars are born in places that older stars are simultaneously tearing apart. The cosmic cliffs show this tension vividly. The towering edge is being sculpted by intense ultraviolet radiation and stellar winds from hot young stars located just beyond the visible frame. That radiation carves cavities in the cloud, evaporates material, and reveals structures shaped like pillars, ridges, and arcs. At the same time, in denser pockets, where gas resists dispersal, gravity can continue its slow work. The result is a region that looks almost alive with contradiction. Destruction and creation are happening together. The same energy that strips material away may also trigger collapse in neighboring zones, helping to form another generation of stars. That matters because star formation is not a minor side story in astronomy. It is one of the central engines of cosmic evolution. Stars forge heavier elements in their cores. Massive stars enrich space when they die. Later clouds incorporate those elements, making rocky planets and complex chemistry possible. To understand where planets and life ultimately come from, we first have to understand how stars are born, how they shape their surroundings, and how one generation sets the stage for the next. Webb's early images made that chain feel immediate. You could look at a dust-filled wall and understand, almost viscerally, that this is not static scenery. It is a threshold. Behind it and within it, gravity is assembling the future. The telescope had transformed a distant nebula into evidence of process. But if the Carina view captured the drama of beginnings, another early target revealed the beauty and strangeness of endings. The Southern Ring Nebula had been observed before, including by Hubble, and even older images already showed it as a luminous shell surrounding a dying star. Yet Webb's view changed the emotional weight of the object almost at once. In near-infrared and mid-infrared light, the nebula became layered, intricate, and unexpectedly personal. Dust glowed, filaments emerged. The structure appeared not as a simple ring, but as a far more complex cloud shaped by past episodes of stellar mass loss. The name Southern Ring Nebula is itself a little deceptive. What we call a ring is a two-dimensional projection of a three-dimensional structure. We are seeing an expanding shell of gas and dust from a particular angle, and that angle tricks the eye into simplifying something much richer. At the center lies a star that has reached the late stages of its life. It was once a sun-like star, not among the most massive in the galaxy, but massive enough to undergo profound changes as it exhausted the hydrogen and helium that fueled its internal balance. Stars live for so long that it is easy to imagine them as permanent, but they are temporary arrangements of pressure and gravity. For most of a star's life, those forces oppose one another. Gravity pulls inward, fusion pushes outward. As long as that balance holds, the star remains stable. When the fuel begins to run low, the balance shifts. Outer layers can swell and drift away. Pulses and winds can drive material outward over immense distances. Eventually, what remains of the core becomes a white dwarf, a dense stellar remnant no longer powered by fusion in the way it once was. The nebula we see around such a remnant is not an accidental haze. It is the star's own outer layers, cast off into space. In visible light, some of this material appears in glowing gas. In infrared, warm dust becomes much more prominent. Webb revealed that dust in remarkable detail, showing shells and clumps that hint at repeated episodes of mass ejection. It also helped distinguish two stars in the central region, making clear that the dying star has a companion. That companion is not just a curiosity. Binary interactions may play a major role in shaping the nebula's structure. When stars orbit one another, their gravitational relationship can influence how material flows, where it accumulates, and what asymmetries develop in the expanding cloud. The result can be patterns far more intricate than a simple spherical shell. So once again, Webb was doing something more than making an old object prettier. It was clarifying the mechanism behind what we see. There is a larger significance to this as well. When stars like this die, they do not simply vanish. They return material to the interstellar medium. Carbon, oxygen, and other elements produced over stellar lifetimes are released back into the galaxy. Dust grains form. Gas cools and drifts. Future clouds, future stars, and future planets inherit that matter. In that sense, the Southern Ring Nebula is not merely a symbol of death. It is part of a recycling system on which later worlds depend. That is one of the quiet themes running through Webb's early observations. The telescope keeps showing that the universe is built from continuity disguised as change. A stellar nursery appears full of beginnings, but it is shaped by the remains of older stars. A planetary nebula appears to mark the end of a life, yet it also seeds the next chapter of cosmic chemistry. Dust is not just obscuration, it is raw material. Gas is not just backdrop, it is inheritance. Even the visual contrast between these early targets carries meaning. In Carina, the scene feels energetic and unresolved. Dense ridges are being blasted, illuminated, and penetrated by young starlight. In the Southern Ring, the mood is more elegiac. Matter drifts outward from a star that has spent most of its useful life and now leaves behind a compact remnant. But the physics links them. The material expelled by one generation becomes part of the environment that helps shape another. Webb's infrared vision lets us see that continuity with unusual clarity. Dust that once hid young stars now glows in a dying nebula. Gas that once looked diffuse gains structure. The life cycle of stars becomes less abstract because the same instrument can study both ends of the process with the same fundamental advantage. It can detect what visible light so often leaves incomplete. That ability also changed how astronomers could talk to the public about these objects. For years, many deep sky images were treated primarily as spectacles, beautiful and inspiring, but often separated in the public imagination from the scientific work behind them. Webb made that separation harder to maintain. The beauty is still there, perhaps more than ever, but the logic is closer to the surface. You can look at one of these images and understand why the telescope needed to work in infrared. You can see that it is revealing the hidden architecture of cosmic change. And that is why these first images mattered so much. They were not just a victory lap for a successful launch. They were proof of concept in the most meaningful sense. Webb had reached its operating environment. It had cooled. It had aligned. And now it was demonstrating that its view of the universe was genuinely different. It could unveil the interiors of dusty stellar nurseries. It could map the warm dust and expelled matter around dying stars. It could turn familiar astronomical objects into deeper physical stories. The effect of that realization spread quickly, because once a telescope proves it can do this nearby, the mind immediately leaps outward. If Webb can reveal hidden stars forming inside local nebulae, what can it show in much larger and more active star factories elsewhere? If it can trace how dying stars recycle matter into space, what happens when entire galaxies undergo furious periods of birth and death at once? If infrared can transform our understanding of these relatively familiar regions, then what happens when we point that sensitivity towards structures vastly farther away, where the light itself has been traveling toward us since the universe was young? That is when the early images stopped feeling like isolated marvels and started to feel like the opening pages of a much bigger investigation. Because the same instrument that could show us the anatomy of stellar birth and stellar death was also preparing to widen the scale until even entire galaxies would begin to look like temporary weather in a universe still holding its oldest secrets just beyond the dust and the dark. And once the scale widens that far, something remarkable begins to happen to your sense of proportion. A nebula can feel immense when you first encounter it, a wilderness of gas and dust stretching across distances no human mind can truly picture. But then Webb pulls back and shows regions where entire nebulae are only pieces of a larger ecological system inside galaxies. And even galaxies themselves become actors inside a much older cosmic drama. What seemed huge begins to feel local. What seemed final starts to look provisional. And this is where Webb's early observations begin to do something especially powerful. They do not just reveal objects, they rearrange the ladder of scale in your mind. A perfect example is the Tarantula Nebula. Even by the standards of star-forming regions, it is extreme. Located in the Large Magellanic Cloud, a satellite galaxy of our own Milky Way, the Tarantula is one of the largest and most active stellar nurseries in the nearby universe. It contains some of the most massive stars known, and the amount of energy pouring out of the region is staggering. To look at it with Webb is to see not a quiet cloud gradually assembling stars, but a turbulent engine room where stellar birth is happening with unusual intensity. The name comes from its web-like appearance, but that only hints at the complexity inside. In infrared light, Webb reveals dense filaments, cavities hollowed out by radiation and winds, compact clusters of hot young stars, and dust-rich zones where future stars remain hidden. The view feels crowded and restless. Everywhere you look, there are signs of feedback, the process by which stars influence the material around them. Massive young stars flood their surroundings with radiation, ionize gas, and drive powerful winds. Those effects can clear out the immediate environment, but they can also compress nearby material, potentially helping new collapse begin elsewhere. This feedback is central to understanding why regions like the Tarantula Nebula matter so much. Star formation is never just about gravity gathering gas into stars. Once the first massive stars ignite, they begin reshaping the cloud that gave birth to them. They can disperse the raw material that might have formed future generations, but they can also organize, compress, and stir it. The environment becomes self-modifying. Starbirth changes the conditions for later starbirth. In that sense, the tarantula is like an amplified version of what Webb showed in the cosmic cliffs. The same underlying ideas are present, but here they are turned up to extraordinary levels. The stars are hotter, the outflows stronger, the cavities larger, the energy budget far more intense. And that makes the region scientifically precious, because it acts as a partial analog for a much earlier time in the history of the universe. Astronomers sometimes refer to a period known as cosmic noon, an era several billion years after the Big Bang, when star formation across the universe was far more vigorous than it is today. Galaxies were richer in gas, interactions were more common, and the cosmos was a much busier place. We cannot visit that era directly, but we can look for nearby environments that resemble some of its conditions. The Tarantula Nebula provides one such laboratory. It is not identical to the ancient universe, of course, but it allows astronomers to study intense star formation in detail, close enough for Webb to resolve structure that would be impossible to separate in much more distant systems. So once again, the telescope is doing more than giving us a beautiful view. It is helping bridge local astrophysics and cosmic history. A star-forming region in a neighboring galaxy becomes a clue to understanding a time when galaxies across the universe may have looked more active, more chaotic, and more fertile than they do now. Webb lets us study that connection in a way that feels almost intuitive. It lets us see that the young universe was not only distant in time, but likely very different in mood. That shift in mood becomes even more dramatic when the focus moves from stellar nurseries to entire galaxies in motion. One of Webb's most compelling early targets in that regard was Stephan's Quintet, a famous group of galaxies first identified in the 19th century. The name suggests a clean family of 5 interacting members, though the true geometry is more subtle. 4 of the galaxies are genuinely involved in a gravitational dance, while 1 lies much closer to us and only appears to belong to the group by line of sight. Even that small complication says something important about astronomy. The universe constantly presents flat projections of deeply three-dimensional reality, and one of our tasks is learning how to read through the illusion. In visible images, Stephan's Quintet is already captivating. In Webb's observations, it becomes something richer and more revealing. Dust lanes glow, shock regions stand out, hidden star formation becomes easier to trace. You begin to see galaxies not as fixed islands of stars, but as systems capable of disturbing one another on colossal scales. Gravity stretches them, warps them, and drives material into new configurations. Interactions between galaxies can trigger bursts of star formation as gas clouds collide and compress. They can also feed central black holes by funneling matter inward. Over long enough timescales, they can transform the very shapes and identities of the galaxies involved. This is one of the great insights of modern cosmology. Galaxies are not isolated ornaments scattered decoratively across space. They evolve through encounter. They merge, accrete, distort, and rebuild. The universe is dynamic not just at the scale of stars, but at the scale of galactic architecture itself. Webb's infrared sensitivity makes that dynamism easier to read. Warm dust, often associated with regions of active star formation or energetic processes near galactic centers, emerges with unusual clarity. Gas that has been shocked by collisions and movement through intergalactic space becomes part of the story. The scene no longer looks like a static portrait. It looks like a system under stress, a record of forces unfolding over hundreds of millions of years. And there is something quietly humbling about that. A single stellar nursery already exceeds human scales by absurd margins. But galaxies interacting with one another push the imagination into a still deeper region of discomfort. Distances widen, timescales lengthen. The very idea of motion becomes difficult to hold in the mind because everything is moving, but moving so slowly in human terms that the drama has to be inferred from structure rather than watched directly. Webb helps make that inference feel concrete. It lets us see the signatures of collision and disturbance frozen in dust, gas, and light. By this point, the documentary logic of Webb's early observations becomes unmistakable. It is as though the telescope is teaching us how to think in expanding layers. First, it shows the birth of stars inside dusty nearby regions. Then it shows the death of stars and the recycling of matter. Then it pulls outward to giant star-forming environments that hint at ancient cosmic conditions. Then it reveals galaxies interacting on scales large enough to reshape whole stellar populations. Each step widens the frame. Each step makes the universe feel less like a collection of isolated objects, and more like a connected, evolving system. And naturally, that widening frame leads toward the deepest ambition of all. If star-forming regions can teach us how matter organizes itself locally, and galaxy groups can show us how large-scale structures evolve over time, then what happens when Webb looks not at a famous nearby object, but at a patch of sky so apparently empty that earlier generations might have passed over it without a second thought? That question sits at the heart of the deep field tradition in astronomy. The idea is simple and almost absurdly bold. Point a telescope at a tiny, seemingly unremarkable area of sky, and stare long enough that the faintest possible sources begin to emerge. What appears empty to the eye, and even sparse to shorter exposures, gradually fills with galaxies. The longer you look, the more the universe confesses that emptiness was never emptiness at all. Hubble had already transformed astronomy with this approach. Its deep field images revealed that countless distant galaxies populated tiny fractions of the sky, each one representing a different era in cosmic history. Webb inherited that legacy and extended it into infrared territory, exactly where the most ancient and red-shifted light should become accessible. The result was astonishing. Webb's first deep field image centered on the galaxy cluster SMACS 0723. At first glance, the cluster itself is impressive, with bright galaxies and distorted arcs of light surrounding it. But those arcs are part of what makes the image so scientifically rich. The gravity of the cluster bends space-time strongly enough to magnify and distort the light of even more distant galaxies behind it. This effect, gravitational lensing, turns massive clusters into natural cosmic lenses. They help telescopes like Webb see objects that might otherwise remain too faint. So the deep field is not just a long exposure, it is a collaboration between instrument and gravity. Webb collects faint infrared light with extraordinary sensitivity, while the mass of the cluster amplifies some of the even more distant background sources. The result is a layered image in which galaxies from multiple eras of cosmic history appear together. Some are relatively nearby in cosmological terms. Others are so distant that we are seeing them from a time when the universe was still in its youth. This is where the phrase, looking back in time, becomes something more than poetry. In one field of view, Webb can capture light that began traveling toward us billions upon billions of years ago. Some of those galaxies appear not as mature spirals or settled ellipticals, but as younger, more irregular structures. Systems still assembling, still forming stars at high rates, still participating in a universe not long removed from its beginning. The implications of this are difficult to overstate. When you look at one of Webb's deep fields, you are not seeing a random assortment of distant objects. You are seeing a compressed historical record. Nearer galaxies represent more recent chapters. Farther ones represent older chapters. The image becomes a kind of temporal cross-section through cosmic evolution. And once that becomes clear, another question naturally rises. How early can we really see? How close to the beginning can any telescope push the record? That was always one of the deepest hopes surrounding Webb. By detecting highly redshifted infrared light, it might identify galaxies from surprisingly early epochs, perhaps earlier than many models once expected to find them in such numbers. And indeed, as observations accumulated, Webb began delivering candidate galaxies from the young universe that immediately energized debate. Some appeared brighter, more massive, or more developed than astronomers had anticipated for such early times. Even when later analysis refined particular claims, the larger pattern remained electrifying. Webb was opening a region of observation where theory and evidence were meeting under new pressure. That is part of what makes the deep field so profound. It is beautiful, certainly. The image glitters with color, arcs, spikes, and layered structure. But the real emotional force lies in what it represents. Humanity built an observatory, launched it into darkness, cooled it nearly to silence, aligned its mirror in space, and then turned it toward a tiny fraction of the sky, only to find that the darkness was crowded with ancient worlds. There is almost a moral quality to that discovery. It reminds us that apparent emptiness often reflects the limits of our instruments rather than the poverty of reality. The cosmos was full all along. We simply lacked the means to perceive how full it was. And yet even this is not the final step. Because once Webb begins revealing remote galaxies and possible structures from the early universe, the question is no longer just how far away these objects are. It becomes what their light can tell us about their composition, their temperatures, their dust, their gas, and the physical conditions under which they formed. Images can show that something is there. But to truly understand what Webb is uncovering, astronomy has to move beyond seeing shapes and start reading light itself. Because some of the telescope's most powerful discoveries begin not when the universe becomes visible, but when that visible glow is broken apart into information hidden inside its spectrum. Some of Webb's most important discoveries do not begin with a dramatic image at all. They begin with a puzzle hidden inside light itself. A cloud may glow beautifully in infrared. A nebula may spread across space in astonishing detail. And a distant galaxy may shimmer at the edge of the visible record. But none of that, by itself, tells you what the object is made of. Beauty can show structure. It cannot directly reveal chemistry. And if you want to understand how stars form, how planets inherit their raw materials, or how life-friendly chemistry might emerge, then structure is only the beginning. You have to learn how to read light as evidence. That is where the story becomes even more interesting, because astronomy often advances most powerfully when it stops asking what can be seen and starts asking what light is trying to say. Webb is exceptional at this. Its sensitivity and precision allow it not only to collect infrared light from faint and distant objects, but to break that light into patterns that reveal what atoms and molecules are present. In other words, the telescope can act not just as an eye, but as a translator. A useful place to begin is with NGC 346, a bright cluster of stars and its surrounding nebula in the small Magellanic Cloud. This is a fascinating target because it offers something more than a beautiful view. The physical conditions there, and especially the relative scarcity of heavier elements compared with regions like our own galactic neighborhood, make it an imperfect but valuable local analog for an earlier era of the universe. Astronomers use places like this to think about cosmic noon, that long, busy age when star and galaxy formation were unfolding far more rapidly than they do today. If you want to imagine a universe younger, more active, and chemically less enriched, regions like NGC 346 can help. But how do scientists actually know what such a nebula contains? Part of the answer lies in emission lines. When gas is heated, whether by nearby stars, energetic shocks, or other mechanisms, the atoms inside it do not radiate just any light at random. They emit light at specific wavelengths determined by their internal structure. Each element carries its own distinctive pattern. Oxygen leaves one kind of signature, hydrogen leaves another. Sulfur leaves another still. The exact physics reaches down into quantum behavior, but the observational consequence is simple. Heated gas writes a chemical fingerprint into the light it emits. That means when Webb observes a glowing nebula, it is not merely recording brightness. It is collecting clues about composition. The telescope can identify which elements are present, and in some cases, infer something about the temperature, density, and behavior of the environment. A cloud of ionized gas stops being just a luminous shape and becomes a physical system that can be interpreted. In NGC 346, this matters because the region is not only chemically interesting, it is also a place where stars are actively forming. Once again, Webb's infrared vision allows it to peer past dust that would frustrate visible observations. Buried within the broader nebula are smaller disks of dust surrounding young, developing stars. These protoplanetary disks are among the most important structures in astronomy because they are the environments from which planets can eventually emerge. Around a newborn star, dust and gas settle into orbiting material. Within that disk, grains collide, stick, grow, and gradually participate in the long process that may produce planets, moons, asteroids, and comets. So now the telescope is doing two things at once. It is using the emitted light of hot gas to read the chemical conditions of a star-forming environment, and at the same time, it is revealing the small, dusty structures around infant stars where future planetary systems may begin to take shape. This is a profound combination. It ties large-scale environment to small-scale consequence. The chemistry of a nebula and the architecture of a forming planetary system are not separate stories. They are stages in the same one. And yet, even emission lines only take us so far. A glowing nebula is generous. It offers light openly. Heated gas announces itself. But not every important structure in the universe is hot enough or bright enough to do that. Some of the most consequential regions in space are cold, dark, and quiet. They do not broadcast their chemical makeup by glowing vividly into the night. If anything, they seem to resist observation. They absorb, obscure, and hide. That is exactly what makes the Chameleon-1 dark molecular cloud so important. This cloud is another stellar nursery, another place where future stars may one day emerge. But in emotional terms, it feels entirely different from the bright, sculpted nebulae Webb showed so spectacularly at first. Chameleon-1 is not a luminous cliff face or a glowing shell around a dying star. It is an icy, dense, dark cloud. The raw materials are there, but they are cold enough that emission line methods alone do not give astronomers what they need. If you want to know what such a cloud contains, you need a different strategy. And this is where astronomy begins to perform one of its cleverest acts. Instead of studying the light the cloud gives off, you study the light it takes away. The logic is elegant. Earlier we considered how atoms and molecules emit radiation when they are excited. But the same basic physics can work in reverse. If a broad, continuous source of light passes through a cloud, atoms and molecules in that cloud can absorb very specific wavelengths. They remove those wavelengths from the passing light. The result is a spectrum with missing pieces, narrow, dark fingerprints that correspond to specific substances. This is absorption spectroscopy. To make that work, you need a background source of light. In the case of a dark cloud, the useful illumination comes from stars behind it. Their light travels through the cloud on its way to us. If the cloud contains water ice, ammonia, methane, methanol, or other compounds, those materials can absorb particular parts of that starlight. Then, by measuring which wavelengths are missing, astronomers can reconstruct the chemistry of the cloud itself. It is an astonishing method when you pause to think about it. The cloud does not need to shine. It only needs to interrupt. Knowledge comes not from what appears, but from what fails to appear. There is, however, a difficulty. Dense molecular clouds can be so thick that background starlight struggles to get through at all. The cloud is not simply dim. It is deeply obscuring. In many cases, the signal is too faint or too compromised to analyze well. And this is exactly where Webb's unprecedented sensitivity becomes decisive. For the first time, astronomers could detect starlight filtering through the thick material of Chameleon-1 strongly enough to read the cloud's chemical fingerprints in detail. What they found changes the emotional tone of the story. The cloud contains water ice. That alone would be important. Water is one of the most central molecules in all of planetary science and astrobiology, and finding it within the frozen material of a star-forming region immediately links the future of planetary systems to chemistry already underway before any planet exists. But Webb did not stop there. It also revealed more complex ingredients, including ammonia, methane, and methanol. That discovery matters because it suggests that the chemistry relevant to later planetary evolution can be present surprisingly early, before a star fully forms, before a planet acquires oceans or an atmosphere, before geology, weather, or biology enter the scene. The molecular groundwork may already exist inside the icy material from which those later worlds will inherit their substance. In other words, planets may not begin as chemically blank objects waiting for interesting things to happen. They may begin with a meaningful starter kit. That does not mean life is inevitable. It does not mean every icy cloud becomes a cradle for biology. But it does change the framework. If the ingredients observed in Chameleon 1 are common in other dark molecular clouds, then the seeds of chemical complexity may be widespread throughout the galaxy, and perhaps throughout the universe. The barrier between cosmic chemistry and planetary chemistry begins to look less like a hard boundary and more like a continuum. This is a subtle but powerful shift. Earlier, Webb showed that stars are born in dusty nurseries and that dying stars return matter to space. Now it is revealing that inside the coldest and quietest parts of that cycle, chemistry may already be organizing itself in ways that matter enormously later on. A cloud is no longer just a future star. It is also a future inventory. And this is why spectroscopy is so transformative. It makes invisible chemistry legible. It lets astronomers move beyond surfaces and silhouettes. A region that looks dark and undramatic can become one of the most information-rich environments in the sky, because within its missing wavelengths lies a story about ingredients, inheritance, and possibility. There is a deeper philosophical point here, too. Human intuition is usually drawn to brightness. We assume the most dramatic truths will reveal themselves in the most luminous places. But astronomy keeps teaching the opposite lesson. Sometimes the crucial evidence lies in the faint signal, the buried structure, the blocked wavelength, the nearly lost background star. Sometimes understanding advances by following absence with enough care that it becomes a form of presence. Webb is particularly well suited to this kind of work because infrared light interacts with dust differently from visible light, and because the telescope is sensitive enough to study weak signals that would once have fallen below the threshold of usefulness. That combination makes it possible to treat dark clouds not as obstacles to observation, but as targets in their own right. Dust no longer just hides the universe. It becomes part of the message. And once you realize that, an entirely new range of possibilities opens up. If the chemistry of a dark cloud can be inferred from the background starlight it absorbs, then the same basic principle can be extended elsewhere. Light can pass through planetary atmospheres and record their composition. It can slip past rings, thin enough to escape direct imaging, and still reveal their presence when a star dims at just the right moment. It can encode information in loss as well as gain. The telescope no longer needs an object to blaze. It only needs the universe to leave fingerprints. This is the moment when Webb's mission deepens again. It is no longer only the great observer of ancient galaxies, or the great revealer of stellar birth clouds, or the great chronicler of cosmic dust. It becomes something almost forensic. It studies traces. It notices what should be there and is not. It turns shadows into evidence. And once astronomy learns to trust that kind of evidence, the telescope can begin reading not only star-forming clouds, but the atmospheres of distant worlds and the signatures of structures too small or too dim to be seen directly. Which means the story is about to move from hidden chemistry in interstellar ice to far more delicate clues written into passing light from planets and rings. Once you begin to trust light in that way, as something that can carry evidence even when an object is not plainly visible, the universe starts to open along entirely new lines. A telescope no longer has to rely on direct pictures alone. It can infer, it can compare, it can notice when a signal shifts by a tiny amount and use that shift to reconstruct a hidden reality. This is one of the quiet revolutions behind Webb's scientific power. It does not only show us what is there, it allows us to investigate what cannot be cleanly seen at all. That is especially important when the target is a planet orbiting another star. For most exoplanets, even the largest telescopes do not capture a tidy image of the world itself. The planet is too small, too faint, and too close to the overwhelming brightness of its host star. Yet, under the right circumstances, there is still a way to learn something intimate about it. If the planet passes in front of the star, from our point of view, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. That atmosphere, however thin or thick it may be, leaves its own fingerprints on the light. This technique sounds delicate because it is. The changes are small, and the measurements demand extraordinary stability and sensitivity. But when it works, it transforms a distant point of light into a world with detectable chemistry. Webb demonstrated that power dramatically with the exoplanet WASP 39b. This is not a gentle Earth-like planet. It is a hot gas giant, broadly comparable in mass to Saturn, but swollen by heat into a much larger size. It orbits its star extremely closely, completing a year in just a few days, and its atmosphere is correspondingly hot and expanded. In some ways, that makes it a convenient first subject for atmospheric study, because an extended atmosphere leaves a clearer signature during transit than a compact one would. Even so, the achievement remains remarkable. We are talking about a planet hundreds of light years away, not as an image with continents and clouds, but as a faint modification of starlight, precise enough to be interpreted chemically. Webb's observations of WASP 39b revealed a spectrum rich with information. Water vapor was detected, carbon dioxide appeared, sulfur dioxide was identified as well, and that result drew particular attention because it pointed to active photochemistry, chemistry driven by the star's radiation. In other words, this was not merely a static atmosphere composed of passive ingredients. It was an atmosphere being transformed by energy, with chemical reactions reshaping what was present over time. That matters for several reasons. On the practical level, it proves Webb can do exactly the kind of atmospheric characterization astronomers had hoped for. It can read the compositions of distant worlds. It can detect molecules. It can begin to distinguish atmospheres shaped by different histories and physical conditions. But on a deeper level, it changes the way we think about exoplanets altogether. For much of human history, planets beyond the solar system existed only as speculation. Then they became detections, mostly through indirect methods. A star wobbled slightly. A transit dimmed its light. A planet was inferred. Later, catalogs filled with thousands of such worlds, and a strange, new cosmic geography emerged. Hot Jupiters hugging their stars. Super-Earths with no direct counterpart in our own system. Dense, compact worlds. Puffy, inflated worlds. But even then, many exoplanets still felt abstract, almost statistical. They were known by their orbital behavior more than by their physical character. Spectroscopy changed that. A detected atmosphere means a world begins to feel less like a number in a table and more like a place with weather, chemistry, and environmental structure. WASP 39b is not a promising abode for life. It is too hot, too gaseous, too hostile in every familiar sense. Yet, that is not why it matters. It matters because if Webb can read an atmosphere like this, then atmospheric study becomes a general pathway. Today, a hot gas giant. Tomorrow, something smaller, cooler, and more challenging. The method scales toward more subtle targets. And once again, the key is not just what the telescope sees directly, but what it infers from missing and altered light. The atmosphere betrays itself by filtering the star's glow. Molecules remove particular wavelengths. The resulting pattern becomes evidence. What we learned in the dark cloud now extends to distant planets. Chemistry can be read across impossible distances if the geometry is right and the instrument is sensitive enough. The same broad principle applies in another Webb result that feels, at first glance, almost magical. This time the target was not an exoplanet orbiting another star, but a small, icy body in our own solar system called Chariklo. Chariklo belongs to a class of objects known as centaurs, bodies that orbit in the outer solar system with characteristics that blur familiar categories. They are not quite like the major planets, not quite like typical asteroids, and not quite like classical comets either. They inhabit a transitional realm, and that alone makes them interesting. But Chariklo carries an additional surprise. It has rings. That is not what astronomers once expected from such a small object. Rings were traditionally associated with giant planets, systems like Saturn's, where large-scale gravity and countless particles create magnificent structures easily visible to telescopes. The discovery that a comparatively modest body like Chariklo could host rings forced a revision in intuition. Apparently, under the right conditions, ring systems are not the exclusive privilege of giants. Webb contributed to that understanding through a technique called occultation. Once again, the method depends not on photographing the structure directly in the way our minds instinctively imagine, but on measuring what happens when a background star's light is interrupted. If Chariklo passes in front of a star, the starlight will dim. If rings surround Chariklo, those rings can produce smaller, earlier, and later dips in brightness as they cross the line of sight, before and after the main body. This is such a subtle form of detection that it almost feels like listening for footsteps in the dark. The rings are not presenting themselves in a grand image. They are announcing their presence through timing and shadow. A slight dimming, then another, then the main occultation, then the reverse sequence as the alignment changes. From this pattern, astronomers can infer the existence of rings and learn about their structure. What makes this so compelling is how it turns absence into geometry. The star briefly loses brightness, and from that temporary loss, a hidden architecture becomes visible. Webb's role here again highlights its extraordinary sensitivity. Precise measurements of small changes in infrared light make it possible to detect structures that would otherwise remain elusive. And the implications stretch outward. If a small centaur can possess rings, then the mechanics of ring formation and persistence may be broader and more varied than older models suggested. How do such rings form? Are they debris from impacts, remnants of disrupted material, or evidence of more complicated dynamical histories? How stable are they over time? Do similar systems exist around other small bodies that we have simply not observed in the right way yet? One careful occultation leads naturally to a much wider field of questions. By now, a pattern is becoming unmistakable in Webb's work. The telescope repeatedly shows that indirect evidence is not second-rate evidence. In many cases, it is the only path available. A distant atmosphere cannot be photographed like a nearby cloud, but it can still be read. A faint ring system around a small outer body may evade direct imaging, but it can still betray itself by briefly dimming a star. The universe does not always reveal its secrets through obvious spectacle. Sometimes it offers only a trace, and the instrument worthy of that universe is one that knows how to treat traces seriously. That idea reaches a kind of visual climax in one of Webb's most arresting observations, the system known as Wolf-Rayet 140. At first glance, the image appears almost unreal. Concentric shells of dust ripple outward from the center like rings on a pond, or grooves pressed into a cosmic record. They are nearly perfect, layered one outside another with haunting regularity. The scene is so geometrically beautiful that it could be mistaken for an artistic rendering. But it is not art. It is a physical history written into dust. Wolf-Rayet stars are already extraordinary objects. They are massive, evolved stars that have shed much of their outer hydrogen, exposing hotter, deeper layers and driving ferocious stellar winds. These winds can carry material away at astonishing speeds. In the case of Wolf-Rayet 140, the system includes not just one star, but a binary pair. The Wolf-Rayet star orbits alongside another massive star, and together they create conditions where their winds collide. That collision is the heart of the pattern. As the stars move through their orbit, there are periods when the geometry and density of the colliding winds allow dust to condense. Then, the radiation pressure and outflow carry that dust outward into space. Because the process repeats with orbital regularity, each major episode produces another shell. Over time, the system creates a layered structure, each ring preserving a past moment of dust production, like a timestamp expanding into the dark. Webb's infrared vision was crucial here because the shells are made of dust, and dust radiates strongly in infrared wavelengths. What might have been faint, incomplete, or easily overlooked in visible light becomes astonishingly clear. The telescope reveals not just one shell, but many, extending far outward from the center. The pattern lets astronomers reconstruct something like a long-term record of the system's behavior. Each ring corresponds to an earlier cycle. The farther out a shell lies, the older it is. There is something deeply moving about that. A binary star system, locked in a powerful orbit, has been writing a repeating signature into space for more than a century. And now, by observing the structure of those shells, we can read that repeating signature backward through time. The image is beautiful, yes, but its beauty comes from order. It is a record of physical process made visible. And notice how perfectly this fits the wider theme. A planet's atmosphere is detected because it modifies passing starlight. A ring system is recognized because it briefly interrupts a background star. A binary dust factory reveals its history because infrared light from expanding shells preserves cycles of hidden interaction. In every case, Webb is reading consequences rather than merely surfaces. It is not passively watching the universe, it is decoding it. This is also why the telescope's discoveries can feel so satisfying even when they are not about the most distant galaxies or the oldest light in existence. Webb was designed in large part to look deep into cosmic history, and it does that magnificently. But along the way, it has become a master interpreter of systems much closer to us. It studies atmospheres, rings, dust, and chemistry not as isolated curiosities, but as parts of a broader truth. The universe is full of structures too small, too faint, too cold, or too obscured to announce themselves directly. Yet they still leave evidence. They still disturb light. They still cast signatures into observation. And once you start thinking this way, you begin to suspect that some of the most important discoveries may emerge not when a telescope confirms what we already expected to find, but when it reveals something that should barely be there at all. Something faint, numerous, and difficult to explain. Something that forces astronomy to stop admiring its own methods and start asking whether the underlying theory itself might be missing a piece. That possibility became very real in one of Webb's most unsettling findings. Up to this point, the telescope had been showing us things that were surprising, beautiful, and scientifically rich, but still broadly compatible with the deeper architecture of modern astronomy. Dusty star nurseries made sense. Dying stars shedding matter made sense. Spectral fingerprints in dark clouds and distant atmospheres made sense. Even the delicate revelation of rings and repeating shells fit within a universe that, however intricate, still obeyed familiar rules. Then Webb looked into the Orion Nebula and found something that seemed to stand at the edge of those rules. The Orion Nebula is one of the best-known stellar nurseries in the sky. It lies relatively close in astronomical terms, and because it is nearby, bright, and crowded with young objects, it has long served as a natural laboratory for studying how stars and planetary systems form. If you want to understand the earliest stages of stellar life, Orion is one of the first places you would look. That is exactly what made Webb's observations there so important. This was not some obscure or exotic corner of the cosmos. This was a region astronomers believed they understood reasonably well. And yet, buried within that familiar environment, Webb found a population of objects that did not fit comfortably into the existing story. These objects came to be known as jumbos, short for Jupiter mass binary objects. The name is deceptively casual for something so provocative. A jumbo is not a star. It is not even a brown dwarf in the ordinary sense, if its mass stays low enough. It is an object with a mass comparable to Jupiter, or at least in that broad planetary regime. More startling still, many of these objects appear in pairs, orbiting one another without any parent star. That last point is where the true shock begins to set in. Binary systems are common in the universe. Many stars are born with partners. Some systems contain 3 or more stars in complex arrangements. At large masses, paired formation is not exotic at all. But as you move downward in mass, the situation changes. Brown dwarf binaries exist, though they are less common. At planetary masses, however, the expectation was that true binary free-floating pairs should be extremely rare, perhaps nearly non-existent under standard formation scenarios. And yet, Webb did not find just one suspicious case in Orion. It found many. To appreciate why this is such a problem, we need to be careful about categories. A planet, in the conventional sense, forms within the disk surrounding a young star. It grows out of the same broader process that produces the stellar system, but it remains gravitationally tied to the star that anchors that system. A free-floating object with a mass similar to Jupiter is already an odd thing. It looks like a planet in mass, but not in circumstance. If such an object roams space without a host star, there are 2 broad ways to think about it. Either it formed like a planet and was later thrown out, or it formed more like a star from direct collapse of gas, only at an unexpectedly low mass. Each of those ideas already carries complications. But the moment you add binarity, the tension rises dramatically. Imagine 2 Jupiter mass objects orbiting each other in interstellar space inside a star-forming region. If they were originally planets in ordinary planetary systems, then somehow each pair must have been assembled in an orbit around its parent star, remained bound to each other, and then been ejected together without being torn apart. That is not impossible in the strictest sense. Chaotic gravitational interactions can do remarkable things. Young planetary systems may be unstable. Massive bodies can scatter one another violently. But the more often you ask for such a delicate outcome to occur, the less persuasive it becomes as a blanket explanation. On the other hand, if these objects formed directly from collapsing gas clouds the way stars do, then another problem appears. There is supposed to be a practical lower limit to how small a fragment of gas can become when it collapses under its own gravity. If the fragment is too low in mass, it cannot cool efficiently enough. Heat builds up. Pressure resists further collapse, and the process stalls. This is one reason astronomers did not expect large numbers of isolated planetary mass objects to form directly from interstellar gas. The physics seemed to impose a floor, so jumbos landed in astronomy like a stone in still water. They disturbed multiple assumptions at once. They were too numerous to dismiss easily. Too low in mass to fit cleanly into star-like formation. Too often paired to fit comfortably into standard planetary ejection stories. And because they were found in Orion, a benchmark nursery rather than some bizarre edge case, they demanded to be taken seriously. The number itself is part of the shock. If Webb had uncovered a single unusual binary planetary mass object, astronomers might have celebrated the oddity while treating it as a curiosity. Rare events happen. Nature always leaves room for outliers. But a substantial population is different. A population suggests process. It tells you that the universe is not merely producing one improbable object once in a while. It is generating them often enough that your framework may be incomplete. That is the point where observational astronomy becomes truly unsettling. Because a telescope does not care whether a theory is elegant. It does not care how long a model has held together, how many papers were built on it, or how intuitively satisfying it feels. If the sky contains something real, and the instrument is good enough to see it, then the burden shifts to theory. And in the case of jumbos, that burden suddenly became heavy. The objects were identified in infrared observations of the Orion Nebula, exactly the kind of environment where Webb excels. Young regions are rich in dust, confusion, and faint sources. Infrared sensitivity is essential for teasing structure out of the crowd. That same sensitivity allowed the telescope to reveal these dim, low-mass bodies, and in many cases, their pairings. Instead of a simple census of young stars and disks, the observations hinted at an unexpected subpopulation drifting through the nursery. That image alone is difficult to shake. A stellar nursery is already a strange place, dense with gas, turbulence, radiation, and the early architecture of planetary systems. Now add to that scene lonely pairs of Jupiter-mass worlds orbiting each other in the dark, untethered to any sun. They feel almost poetic at first, the sort of objects science fiction might invent to deepen the mood of a cosmic setting. But their significance is not poetic. It is technical and severe. They are a challenge to mechanism. And that brings us to this central question. What are these things, really? The obvious temptation is to reach for language first. Call them rogue planets. Call them failed stars. Call them planetary mass brown dwarfs. But naming is not explaining. A label can soothe the mind while leaving the physical mystery intact. The real issue is not what category feels most comfortable. It is how such objects came to exist in the first place, and why they appear in binary systems often enough to matter. Astronomy has faced this kind of pressure before. Again and again, observations have revealed a population that ought to have been marginal, but turns out to be important. Pulsars once seemed almost unbelievable. Exoplanets transformed from speculation into abundance. Dark energy emerged from measurements that, at first, seemed to point the wrong way entirely. The lesson is not that every surprising result overturns everything. Often it does not. The lesson is that reality has a habit of exposing the hidden assumptions inside our neatest explanations. Jumbos seem poised to do exactly that for theories of star and planet formation. Part of the difficulty comes from the gap between how stars form and how planets form. Stars begin in molecular clouds, where dense regions collapse under gravity until a protostar emerges. Planets are usually thought to form later within the disk around that star, through bottom-up processes such as core accretion, or in some cases, more direct instabilities in the disk. These are not just different scales of the same event, they are different physical environments with different constraints. Jumbos appear to sit awkwardly between them. Their masses point toward planets, their isolation points away from conventional planets, their pairings point toward binary formation. Their low masses resist ordinary binary star logic. This is why the discovery felt so destabilizing. It was not merely adding another strange object to astronomy's catalog. It was exposing a seam between categories we may have treated as more complete than they really are. And Orion is exactly the sort of place where that seam matters most. In a young region, processes are still fresh. Disks are present. Ejections may still occur. Fragmentation of gas clouds is part of the environment. If you are ever going to catch nature in the act of producing borderline objects, a stellar nursery is where you would hope to find them. Webb's observations suggest that Orion may be one of the places where the universe reveals that it has more than one way of making low-mass bodies, or at least one way we have not yet properly understood. There is also an emotional reason this discovery lands so hard. Much of astronomy's beauty comes from pattern. We take comfort in cycles of stellar birth and death, in elegant spectra, in gravitational lensing that obeys relativity, in rings and shells that preserve the memory of past events. Even when the universe is wild, it often feels intelligible. Jumbos interrupt that feeling. They are not just beautiful or distant, they are awkward. They do not slide naturally into the pattern. That awkwardness is scientifically precious. Because once the telescope has shown you that such objects exist, the next task is unavoidable. You have to test the possible explanations. Were these planetary mass bodies born around stars and later ejected in pairs through violent gravitational encounters? Or did they form directly out of gas, despite the apparent lower limits that should have made that difficult? Each possibility sounds plausible from a distance. Each begins to fray when examined closely. And somewhere inside that fraying, Webb may have forced astronomy to confront a missing ingredient in one of its oldest formation stories. The first explanation seems straightforward because it begins from something astronomers already know can happen. Young planetary systems are not always quiet, orderly places. In their early lives, they may contain multiple giant worlds, massive disks of gas and dust, migrating bodies, and unstable gravitational relationships. Over time, these systems can become chaotic. Planets tug on one another, orbits cross, close encounters exchange energy. In the most violent cases, one or more planets can be flung outward entirely, cast into interstellar space as free-floating objects. So, when jumbos appeared in Orion, many researchers naturally asked whether that was all we were seeing. Perhaps these were simply planets that had once belonged to stars and were later ejected. At first glance, this has real appeal. It preserves the familiar division between stars and planets. Stars still form from collapsing gas clouds. Planets still form in circumstellar disks. Jumbos would then be planets by birth, even if they no longer orbit a star. The universe would not need a fundamentally new formation channel. It would only need a chaotic enough one. And certainly, chaos is not in short supply inside a young stellar nursery. Picture a newly formed system crowded with giant planets, still shifting through residual gas. Their gravitational pulls can create instabilities that amplify over time. One close encounter can alter an orbit just enough to set up another. Resonances may break. Migration through the disk can push worlds into dangerous configurations. In such an environment, ejection is not some exotic miracle. It is a recognized outcome of dynamical evolution. But the problem begins the moment we ask this scenario to produce not just free-floating planets, but binary free-floating planets. A single planet can be ejected rather violently and still make sense within the framework of gravitational scattering. A pair of Jupiter mass objects bound to one another is a very different demand. For such a pair to arise from a conventional planetary system, the two bodies must somehow end up orbiting each other while also being removed from the star's control. That means their mutual gravitational bond must survive a turbulent dynamical event strong enough to unbind them from a much larger system. This is where intuition begins to protest. Ejection is a disruptive process. It tears systems apart. It does not, by default, package two low-mass bodies into a stable duet and send them away together. There may be special circumstances in which that can happen. Perhaps two planetary mass objects form in a particular configuration, perhaps within a wider unstable architecture, and are scattered outward as a pair. But once you rely on such delicacy, frequency becomes the issue. Rare outcomes are one thing, a significant population is another. That distinction matters enormously. The case for the ejection hypothesis is much stronger if one or two odd binaries are found. Nature can always surprise us once. But if Orion contains many jumbos, and if a notable fraction of them are binaries, then the mechanism producing them cannot be too fragile or too exceptional. It has to work often enough that the improbable starts looking routine. That is where the ejection picture begins to strain. There is another difficulty as well. In a typical planetary system, giant planets form in a disk around a star. Their architecture is shaped by that disk, by migration, and by the star's dominant gravity. To produce a binary pair of planetary mass bodies, the system must first either generate such a pair or allow two objects to become bound to one another under the right conditions. But planetary formation models are not naturally optimized for building equal mass, mutually bound pairs that later escape together. Once again, this does not mean it cannot happen. It means the path is awkward, and awkward paths must be tested against observed abundance. This is why the ejection idea, while plausible in principle, starts to look unsatisfying when asked to carry the whole weight of the discovery. It explains mobility. It does not comfortably explain multiplicity. It preserves the basic theory, but only by leaning heavily on outcomes that may be too uncommon to match what Webb seems to have found. So the second explanation becomes impossible to ignore. Perhaps jumbos were never planets in the usual sense. Perhaps they formed directly from interstellar gas, more like stars do, but on a much smaller scale. That possibility has an immediate advantage. Binary formation is common when objects form by fragmentation and collapse. If the parent structure breaks into two clumps, or if gravitational instability leads naturally to paired formation, then the existence of binary systems does not feel like an afterthought. It becomes expected. In that sense, direct formation could explain one of the most unsettling features of jumbos far more naturally than ejection does. And yet, this path runs straight into one of the most important theoretical barriers in the field. There is believed to be an effective lower limit to the mass at which a fragment of gas can collapse under its own gravity to form an isolated object. The issue is not gravity alone. It is cooling. As gas collapses, it heats up. If it can radiate that heat away efficiently, collapse can continue. If not, pressure builds and resists further compression. This is often described in terms of an opacity limit for fragmentation. Once a fragment becomes too opaque to its own radiation, it traps heat and struggles to contract into smaller, self-gravitational bodies below a certain mass scale. The exact threshold depends on assumptions and conditions, but the broad expectation has long been that directly forming isolated objects down in the Jupiter mass regime should be very difficult. Not impossible in every imaginable environment, perhaps, but disfavored enough that large numbers of such bodies were not the standard prediction. So here the problem reverses. Direct formation explains binary companionship more gracefully, but has trouble reaching the low masses Webb appears to be seeing. This is what makes the jumbo question so scientifically rich. Each major explanation solves one part of the problem and worsens another. Ejection is comfortable with planetary masses. After all, giant planets undeniably exist. But it stumbles over the repeated existence of binary pairs. Direct collapse is comfortable with binaries, because nature often forms objects in pairs through fragmentation. But it stumbles over the low masses, because the thermal physics of collapsing gas should resist making such tiny, isolated bodies in substantial numbers. When two explanations fail in opposite directions, it often means the real answer may involve a missing ingredient, rather than a simple victory for one side. That missing ingredient may lie in the microphysics of the gas itself. Among the more intriguing ideas revived by the jumbo discovery is the possibility that magnetic effects could alter the standard picture. Decades ago, some theoretical work suggested that magnetic fields in collapsing molecular clouds might help remove angular momentum or otherwise influence fragmentation in ways that change the mass scale of the resulting objects. Under certain conditions, this could, in principle, allow smaller bodies to form than simpler, non-magnetic estimates would suggest. This is not yet a neat, final answer waiting to be stamped into textbooks. It is more like a doorway reopened by observation. The older ideas were interesting, but without compelling observational pressure, they remained speculative possibilities among many. Webb has changed the pressure. Once the sky begins presenting a genuine population of low-mass binary free floaters, mechanisms that were once peripheral suddenly deserve renewed attention. And magnetic fields are not the only possible missing factor. The environment of a stellar nursery is complicated. Radiation from nearby massive stars can influence cloud structure. Turbulence can create density fluctuations across many scales. Disks may fragment under some conditions. Dynamical encounters may occur in crowded clusters. It is entirely possible that jumbos do not arise from one clean universal pathway, but from a mixture of channels whose relative importance depends on the local environment. Some may be ejected, some may collapse directly, some may emerge through a hybrid process we have not fully characterized. But even if the ultimate explanation turns out to be mixed, Webb has still changed the terms of the debate. Before, the boundary between planets and stars seemed conceptually neat. Planets formed in disks around stars, stars formed from collapsing clouds. Brown dwarfs occupied an already interesting middle ground. Now the lower edge of that middle ground looks less settled. Objects with planetary masses may form outside the familiar planetary route more often than expected. Or planetary systems may be capable of producing binary escapees more readily than models suggest. Either way, the categories are no longer as clean as they appeared. That has consequences far beyond Orion. If jumbos are real and common in at least some nurseries, then the census of low-mass objects in the galaxy may be incomplete. There could be many more free-floating bodies than once assumed, drifting through interstellar space unnoticed because they are faint, cold, and difficult to detect. Their total contribution to the population of the galaxy may still be modest in mass, but enormous in conceptual importance. They would represent a class of object that forces us to rethink how often nature forms worlds without suns, or sunless bodies that only resemble worlds by mass. There is also a deeper lesson here about how astronomy progresses. We often imagine that knowledge accumulates by filling in empty boxes. One more galaxy catalogued, one more atmosphere measured, one more nebula resolved. And sometimes that is true. But the most consequential discoveries often do something rougher than that. They expose where the boxes themselves were drawn too neatly. They show that the map was organized around assumptions that reality never agreed to honor. Jumbos have that quality. They arrived not as a complete contradiction to everything we know, but as a disturbance at the edge of our confidence. They live in the seam between formation theories. They force dynamicists, planet formation experts, and star formation theorists into the same uncomfortable room. They do not permit an easy answer, because every answer seems to preserve one part of the evidence at the expense of another. And that is exactly why they matter so much. Webb was built to look at the early universe, to study the first galaxies and trace the history of cosmic structure back toward the beginning. It is doing that, but in Orion, much closer to home, it may have done something just as revealing in a different sense. It may have shown that even in one of astronomy's best studied nurseries, we still do not fully understand how nature populates the low mass end of the cosmic family tree. The telescope did not merely discover a strange object. It discovered a pressure point in theory. That is the kind of discovery that lingers, because once a pressure point has been found, everything around it begins to shift. New surveys become more urgent. Simulations have to be rerun under different assumptions. Old theoretical papers gain new relevance. Definitions that once felt stable start to wobble. And beneath all of it is a more unsettling possibility. If the universe can produce objects like these in ways we did not anticipate, then what else have we mistaken for absence simply because our theories taught us not to look for it? That question may be the most honest way to understand what the James Webb Space Telescope has really done to astronomy. It has not simply extended our vision. It has altered our sense of what deserves to be asked. Before Webb, many of the universe's most tantalizing regions were either too obscured, too faint, too distant, or too cold to examine with the depth scientists wanted. There were hopes, of course. There were models, predictions, and carefully reasoned expectations. But expectation is not the same as contact. Webb has turned expectation into confrontation. It has forced theory to stand in the presence of new evidence, and in several cases, that evidence has been richer, stranger, and more consequential than anyone could comfortably assume in advance. That is why the telescope's greatest achievement cannot be reduced to a single image, a single target, or even a single branch of astronomy. Its power lies in the continuity of what it has revealed. In one direction, it reaches backward into cosmic history, toward galaxies whose light began traveling when the universe was still young and unsettled. In another, it peers into dense clouds where stars are only beginning to gather themselves. In another, it studies the cast-off layers of dying suns, the chemistry hidden in dark ice, the atmospheres of worlds too distant to see directly, the rings of small wandering bodies, the concentric memory of colliding stellar winds, and the existence of free-floating objects that seem to fall between the categories we thought we understood. At every scale, Webb keeps performing the same deeper act. It takes beauty and turns it into evidence. That may sound simple, but it is not. Astronomy has always had a dual character. It is one of the most visually arresting sciences, filled with images that stir something immediate and emotional in us. At the same time, it is an interpretive science, one that depends on careful measurement, spectral analysis, timing, geometry, and theory. The danger is that the beauty can sometimes make the science feel passive, as though the universe is merely offering scenes for us to admire. Webb dissolves that illusion. Its images are beautiful precisely because they are structured by physical process. Their grandeur is not decorative, it is diagnostic. The cliffs in Carina are beautiful because they record radiation shaping gas and dust while young stars push into view. The southern ring is beautiful because it preserves the layered outflow of a dying star, giving its matter back to space. The Tarantula Nebula is beautiful because it reveals star formation under fierce conditions that echo a more active young universe. Stephan's quintet is beautiful because its galaxies are caught in the middle of mutual disturbance, and that disturbance is written into their dust and light. The deep field is beautiful because it is crowded with ancient worlds that turn a patch of apparent emptiness into a historical archive. And then the beauty gives way to something even more powerful. Spectroscopy reads chemistry where images alone would stop at appearance. Emission lines tell us what heated gas contains. Absorption lines reveal what a dark cloud has taken from passing starlight. An exoplanet atmosphere, invisible as a place in the ordinary sense, becomes chemically legible because molecules filter a star's light in subtle but measurable ways. A ring system around a small centaur is discovered because a star briefly dims at just the right moments. Dust shells around Wolf-Rayet 140 become a record of repeated orbital interaction. Even the jumbos in Orion emerge as more than curious faint dots. They become a direct challenge to the mechanisms we thought governed the making of stars and planets. That is the pattern worth holding on to. Webb does not simply show more of the universe. It makes the universe harder to simplify. In some ways, that is the highest compliment a scientific instrument can earn. A lesser observatory might fill in details within an already stable picture. A great one does more. It sharpens the picture until the old frame no longer fits as comfortably as before. It reveals that what looked like settled knowledge may have depended on blind spots built into previous generations of data. It does not erase earlier astronomy. Hubble remains foundational. Ground-based telescopes remain essential. Decades of theory remain deeply valuable. But Webb changes the balance between confidence and uncertainty. It gives us stronger evidence, and with that strength, a clearer view of where our understanding is still unfinished. There is something quietly humbling in that. Human beings often imagine progress as the gradual shrinking of mystery. We learn more, explain more, and in doing so, make the unknown retreat. Science certainly does that in one sense. Webb has answered real questions. It has shown that infrared observation can unveil star formation inside dusty regions with extraordinary clarity. It has confirmed and expanded the power of atmospheric spectroscopy for exoplanets. It has traced chemistry in clouds and structures in ancient galaxies. These are genuine gains. But progress in science also has another shape. Sometimes the better we see, the more sophisticated the mystery becomes. The early universe is a good example. For generations, the phrase "first galaxies" carried an almost mythic aura. It referred to a realm that theory could sketch, but observation could only approach indirectly. Webb has moved that boundary. It is now delivering observations from astonishingly early cosmic times. And with them comes a new class of questions. How quickly did the first large structures assemble? Why do some candidate early galaxies appear brighter or more mature than expected? Which early claims will survive further analysis, and which will be refined into subtler truths? We are no longer staring into ignorance from afar. We are inside the debate now. The same is true much closer to home. Before Webb, a region like Orion could feel familiar enough that the broad outlines of the story were secure. Then, a population of free-floating Jupiter mass binaries appears, and suddenly, the low-mass end of formation theory becomes unsettled. That is not a failure of astronomy. It is one of its healthiest moments. A theory is strongest not when it avoids challenge, but when observation is good enough to locate where the challenge truly lies. In that sense, Webb has become more than a telescope. It is a pressure device. It applies observational pressure to some of the most important stories we tell about the cosmos. How do the first galaxies emerge? How do stars shape the clouds that form them? How early do chemically rich ices appear in the path toward planets? What do distant atmospheres look like under intense radiation? How common are rings, shells, and other hidden structures when our instruments become sensitive enough to read them? How does nature populate the boundary between planets, brown dwarfs, and stars? The remarkable thing is that these questions are not isolated. They belong to one continuous narrative about complexity in the universe. Gas collapses into stars. Stars alter gas. Stars die and return enriched matter to space. Dust enters clouds. Clouds carry chemistry. Disks assemble around young stars. Planets emerge from those disks, or perhaps sometimes objects of planetary mass emerge by other routes entirely. Galaxies grow, collide, and evolve. Light travels across expanding space, stretched into infrared, carrying records from every stage of this process. Webb meets that light and turns it into a story we can begin to read. That word "begin" is important. For all its power, Webb is not the end of the story. It is an opening. Some of its most important observations will take years to fully interpret. Candidate early galaxies will be scrutinized. Models of formation and feedback will be revised. More exoplanet atmospheres will be studied. More dark clouds will be surveyed. The census of low-mass, free-floating bodies may expand or grow more precise. The telescope's instruments will continue pulling signal out of places that once seemed unreachable, and each new result will feed back into the larger machinery of astronomy. And all of this is happening with an observatory whose lifespan was always expected to be limited. That fact returns us to the paradox at the beginning. Humanity spent decades designing and building a telescope that could never be serviced the way Hubble was, that had to unfold perfectly in deep space. that relies on a finite fuel budget and that exists in a cold, remote balance beyond Earth. By ordinary instincts, it is too fragile, too temporary, too expensive, too risky. And yet, those instincts miss what science sometimes values most. Not permanence, access. A temporary window can still change our relationship to reality forever if it opens onto something we have never truly seen before. Webb has opened that kind of window. It has shown that the ancient universe is not beyond reach. It has shown that dust is not merely obstruction, but archive and raw material. It has shown that darkness can contain chemistry, that absence in a spectrum can reveal hidden substances, that a distant atmosphere can be studied by the way it filters light, that a small body can carry rings, that stellar winds can inscribe history into expanding shells, and that even in familiar nurseries, the cosmos may be producing objects our categories are not ready for. Most importantly, it has reminded us that the universe is not obliged to remain tidy just because our theories are. The cosmos is older, deeper, and more inventive than any single model can comfortably hold at once. Webb's gift is not only that it helps us see this more clearly, it is that it makes the discomfort productive. It turns uncertainty from a void into a frontier. And perhaps that is why the telescope feels so moving. Not only because of the images, though those are unforgettable. Not only because of the engineering, though that achievement is extraordinary. But because Webb captures something central to the scientific spirit. We build delicate instruments and send them into darkness, not because we expect the universe to flatter our expectations, but because we hope it will tell us the truth. Even if that truth is stranger than we imagined. Especially then. The farther Webb looks, the more history it gathers. The more carefully it listens, the more hidden structures emerge. And the more clearly it reveals the universe, the more we are forced to admit that clarity does not end wonder. It deepens it. Because out there, in the infrared glow of ancient galaxies, in the ice of dark clouds, in the breath of distant atmospheres, and in the lonely orbit of worlds without suns, the cosmos keeps offering the same answer in different forms. There is far more going on than we knew. And now, at last, we have begun to see enough to understand how much remains unresolved.